the Oregon coast showing signs of an impending eruption. But scientists say you needn't worry.
It's one of the coolest things that happens on our planet.
News has just broken that the US Geological Survey has issued a red alert for a submerged volcano off the Oregon coast after a sudden swarm of thousands of seismic tremors revealed intense unrest. Deep below the Pacific surface, something powerful is stirring. Seismic instruments are registering a dramatic uptick in quake activity. Deformation sensors are detecting bulging of the seafloor, and scientists are watching closely, uneasy about what might come next. Before we start, smash the like and subscribe buttons for more updates. The volcano in question is Axial Seamount, a submarine volcano located roughly 300 miles off the Oregon coast along the Juan de Fuca Ridge. It sits nearly a mile, roughly 4,900 feet beneath the ocean surface, which means its dynamics are very different from volcanoes on land. Yet, despite its remote setting, it has long been under vigilant watch. It is one of the more well-observed underwater volcanoes, equipped with instruments and cables that monitor seismic tremors, pressure changes, and deformation. Now, that monitoring network is lighting up, signaling that the volcano is far from quiet. This sudden seismic surge appears unprecedented in its intensity. On one day alone this year, more than 2,000 earthquakes were registered around the volcano, a level of activity far above its baseline. Since then, the quake count has waxed and waned, but the pattern remains stark. The seafloor is rumbling and magma may be pushing upward. The volcano is inflating like a balloon as molten rock accumulates in subterranean chambers, pushing upward pressure against the overlying rock and creating strain fractures. That inflation deforms the seafloor, adding further stress and likely triggering many of the earthquakes as rock cracks, slides, or shifts. For decades, Axial Seamount has exhibited a rather repeatable cycle of inflation, seismicity, and eruptions, with known eruptions in 1998, 2011, and 2015. Researchers have long speculated that volcanoes like this might behave in somewhat rhythmic patterns, where magma supply builds over time until a tipping point is reached. But such cycles are rarely so simple or reliable, and Axial's current flurry suggests that we are observing that cycle in action, or perhaps in overdrive. Issuing a red alert is no trivial decision. It means that scientists believe eruption is either underway or imminent, and that dangerous volcanic phenomena could occur. Underwater eruptions don't resemble those on land. Rather than towering ash plumes burying towns, submarine eruptions tend to be more effusive, producing lava flows along the sea floor, venting gases, and sometimes triggering local disturbances in water pressure and temperature. Because it lies deep, the potential for dramatic surface hazards, such as pyroclastic explosions or widespread tsunamis, is generally limited. Still, the underwater world itself could see dramatic disruption. One crucial implication is the pressure on forecasting. The current quake swarm raises questions about how well scientists can forecast underwater eruptions. Unlike terrestrial volcanoes, where visual cues and gas emissions can be seen or sampled, underwater volcanoes pose challenges of indirect measurement. The instrumentation at Axial, tilt meters, pressure recorders, seismometers, is state-of-the-art, but interpreting that data in real time is complex. The red alert suggests that the scientists have judged the signals strong enough collectively to signal high danger. Another implication is for volcanology as a whole. Submerged volcanoes are less well understood than their land-based counterparts. This event offers a rare chance to observe how deep-sea eruptions unfold. It may help refine models of magma transport, rock failure under high pressure and cold water, and how eruption dynamics differ in the presence of ambient water pressure. Lessons learned here could influence how we monitor submarine volcanoes globally, from mid-ocean ridges to underwater hotspots. From a tectonic standpoint, the activity also underscores the interplay between spreading centers, magma supply, and volcanic stress. Axial lies directly along a mid-ocean ridge where tectonic plates diverge. That means the volcano's behavior is shaped not only by the magma chamber itself, but by the regional stress field and the rate at which new magma is being supplied. A surge in magma influx or a change in tectonic strain could tip a delicate balance and trigger new fractures or diking events. The recent quakes might be signs of that interplay. Magma pushing into new cracks, fracturing rock, and triggering seismicity as the system rearranges. The red alert may also amplify public and scientific attention on funding for ocean observatories and monitoring infrastructure. The network that allows scientists to detect and evaluate this unrest does not come cheap. Maintaining underwater cables, seafloor sensors, and data transmission is complex and vulnerable to damage, drift, or instrument failure. In the absence of robust monitoring, a volcano like Axial could be rising toward eruption without warning. Thus, this event highlights the critical importance of investments in rigorous, continuous geophysical monitoring. From a hazard communications perspective, though the volcano is underwater and distant from shore, the issuance of a red alert changes how agencies and communities respond. Mariners near the area may be warned, and oceanographic expeditions scheduled nearby might be diverted. Researchers who work along the Pacific Northwest seafloor may have to reassess risk. Although the likelihood of damage at distance is low, the possibility of localized hazards, disturbances in water columns, gas release plumes, or pressure anomalies cannot be dismissed. In that sense, even remote volcanic unrest carries ripple effects for planning, safety, and maritime operations. Scientifically, the swarm raises tantalizing questions. Has magma pierced a new conduit? Is a dike intruding laterally? Are we witnessing pre-eruption degassing and pressure relief? Which thresholds will be crossed first? Mechanical failure of overlying rock or pressure rupture in the magma chamber? The data currently streaming in will be parsed intensely by volcanologists, geophysicists, and modelers, all racing to anticipate what the volcano might do next. The timing also matters. Some projections suggest an eruption could occur before the end of 2025. That window is narrowing, given the swelling seismic signals. But even so, the volcano may stall, fluctuate, or reconfigure pathways and never erupt in that interval. Volcanoes are notoriously capricious, yet, even short of eruption, the current unrest is itself a remarkable natural event, one that carries lessons about stress accumulation, magma plumbing, and rock behavior under extreme conditions. As the red alert persists, every tremor, tilt change, and pressure shift will be scrutinized. If magma continues to ascend, subtle signals, such as increased microseismicity, accelerated uplift, or changes in gas composition if venting begins, may emerge. Those signals could help bridge the notoriously wide gap between unrest and eruption. Should eruption begin, the process may unfold in phases: intrusion of magma, seepage into fractures, lava spreading across seafloor, and eventual equilibration with ambient pressure. Monitoring those steps in real time could yield new understanding of submarine volcanism's rhythms. Looking more broadly, the event underscores that volcanic risk is not only a terrestrial matter. The oceans conceal dynamic forces that may be less visible but equally consequential in their own domains. Submarine volcanoes host unique ecosystems, hydrothermal vents, and delicate marine biogeochemical cycles that can be disrupted by eruptions. The unfolding drama at Axial could impact microbial communities, seafloor fauna, and chemical gradients. Though these do not draw headlines like ash and lava flows, they are part of the living tapestry of Earth's volcanism. In sum, the red alert marks a pivotal moment. A submerged volcano, long watched yet rarely in crisis, is now trembling with intensity. The subterranean forces of magma, pressure, fracture, and tectonic stress are converging in a drama played out beneath kilometers of water. For scientists, it is a chance to peer into the mechanics of deep volcanoes. For monitoring agencies, it is a stark reminder of the cost and necessity of vigilance. And for communities and mariners, it is an alert that the planet's inner heat moves not just under mountains, but beneath the waves, in places unseen but potent. The deep rumblings beneath the Pacific have continued to mesmerize scientists, drawing renewed attention to the dynamic forces shaping the planet's oceanic crust. As seismic readings climb, each quake becomes another note in a powerful and complex symphony orchestrated by Earth's internal heat. The USGS Red Alert underscores the volatility of this underwater realm, where magma ascends through fractures in the seafloor, forging new crust and reshaping the oceanic landscape in real time. The Oregon offshore region, once quiet and remote, now stands as the stage for one of the most significant geological events of the decade. At the heart of this unfolding drama lies the immense heat energy welling up from Earth's mantle. Beneath axial seamount, molten rock is thought to be accumulating within chambers several kilometers below the seafloor. As magma rises, it heats the surrounding rock, increasing pressure and reducing the density of the crust above. The resulting stress triggers a cascade of micro-earthquakes, each a small crack relieving pressure but simultaneously signaling the relentless movement of magma upward. In this subterranean ballet, tension builds until something gives way. Either magma finds a path to the surface or it stalls, inflating the crust even more. The USGS warning is not merely a call for caution. It is an acknowledgement of how powerful and unpredictable submarine geology can be. Unlike terrestrial volcanoes, which can exhibit visible precursors such as plumes or fumaroles, underwater volcanoes communicate in subtle vibrations, temperature shifts, and pressure waves. Sensors along the seafloor, connected by fiber optic cables, capture these fluctuations in near real time. That network, established through collaborations between the National Science Foundation, Oregon State University, and the University of Washington, is among the most sophisticated in the world. Yet, even with this technology, interpreting the volcano's language remains a challenge. Every swarm of quakes could represent anything from simple crack formation to the imminent movement of magma into new conduits. The implications for the oceanic environment are profound. Submarine eruptions reshape the terrain, forming new vents, ridges, and lava plateaus. When magma contacts seawater, it quenches rapidly into glassy pillow lavas, rounded, blister-like formations that expand across the seabed. These formations create entirely new habitats for microbial life. Chemosynthetic organisms, species that draw energy from chemical reactions rather than sunlight, thrive in the aftermath, feeding on hydrogen sulfide and methane emitted from hydrothermal vents. In this way, volcanic eruptions serve as both a destructive and creative force, annihilating some life while nurturing others in an explosion of elemental energy. One of the most striking elements of this ongoing episode is how it redefines our understanding of geological time. On human scales, these tremors feel sudden, but on the planet's timeline, such events are expressions of long-term cycles that have shaped Earth for billions of years. Axial seamount and its surrounding ridge system represent part of the process by which new crust is continually formed, a conveyor belt of creation moving outward from the ridge as tectonic plates diverge. Each eruption adds another layer of basalt to the ocean floor, extending the Pacific Plate incrementally westward. The red alert thus signals not just a potential eruption, but also a step in the grand continuum of Earth's geological evolution. Beneath the excitement and scientific opportunity, however, lies an undercurrent of concern about what this means for the broader Pacific Northwest. Although a submarine eruption would not directly threaten coastal communities, it is a reminder that this region sits atop one of the planet's most intricate tectonic junctions. The Cascadia Subduction Zone, where the Juan de Fuca Plate slides beneath the North American Plate, has long been a source of anxiety for seismologists. The current unrest offshore reflects how active and volatile the entire system remains. The stresses that drive undersea volcanoes and spreading ridges are intertwined with those that accumulate along the subduction interface. In other words, while axial seamount's activity is localized, it is a symptom of a much larger tectonic pulse running through the Pacific Rim. The chain reaction of earthquakes in the area also sheds light on how energy transfers through rock layers. Each tremor, however small, redistributes stress to adjacent faults. These stress changes can sometimes trigger additional quakes or open pathways for magma migration. Seismologists use advanced computer modeling to simulate these processes, mapping the progression of seismic energy over time. The models from this ongoing event suggest that the quakes are clustering along a network of fissures running northeast-southwest across the caldera, a telltale sign of magma intrusion. If magma continues to migrate, scientists might eventually observe deformation patterns consistent with a dike intrusion, where molten rock wedges itself laterally through the crust. Beyond scientific circles, the red alert has drawn global interest from those fascinated by natural phenomena. The notion of an invisible volcano shaking the ocean floor conjures a mix of awe and unease. It challenges the human perception of stability, reminding us that the planet beneath us and beneath the sea is alive with motion and change. That realization can be both humbling and thrilling. reinforcing the delicate balance upon which modern civilization rests. Every continent, every ocean basin is part of this restless machine, driven by forces that operate on scales far beyond human control. The monitoring of such activity has also sparked innovation in technology. Engineers are experimenting with new autonomous submersibles equipped with AI-assisted navigation systems capable of withstanding the extreme pressures and temperatures of deep-sea environments. These machines could soon venture into the caldera, collecting samples, measuring gas emissions, and mapping topographic changes in real time. Such missions not only expand our knowledge of volcanic behavior, but also refine engineering techniques that could one day be used in extraterrestrial exploration. The oceans, in many ways, are our training ground for understanding the volcanic worlds of other planets and moons, such as Jupiter's Io or Saturn's Enceladus. From an ecological perspective, the quakes and possible eruption could also alter local ocean chemistry. Hydrothermal fluids released during volcanic activity contain metals like iron, manganese, and copper, which disperse through ocean currents. These nutrients can fertilize nearby waters, influencing plankton growth and cascading through the food chain. However, too much of these minerals or a rapid release of volcanic gases like carbon dioxide or hydrogen sulfide can also create zones of low oxygen, a condition deadly to many marine organisms. Scientists studying Axial's ecosystem are particularly interested in how these chemical shifts unfold in the days and weeks surrounding an eruption, hoping to understand the resilience of deep-sea environments. Meanwhile, the physics of underwater eruptions is itself a source of fascination. At depths exceeding 1,500 meters, immense hydrostatic pressure prevents explosive degassing, the violent release of steam and gas that characterizes surface volcanoes. Instead, magma extrudes more smoothly, cooling into solid rock almost instantly. This pressure suppression makes submarine eruptions eerily silent in human terms. There are no fiery fountains or booming explosions, only subtle thermal and acoustic signals recorded by instruments. Yet the volume of lava produced can be immense, covering several square kilometers of seafloor. In effect, the ocean hides cataclysms that would be apocalyptic if they occurred on land. The implications extend to the realm of climate science as well. Underwater eruptions contribute carbon dioxide and other gases to the ocean atmosphere system, though on a smaller scale than continental volcanoes. Still, quantifying their contribution is crucial for understanding long-term carbon cycles. Researchers suspect that submarine volcanism may play an underappreciated role in regulating Earth's climate over geologic timescales, releasing gases that influence ocean acidity and atmospheric composition. The current unrest near Oregon offers a rare opportunity to directly measure such emissions, thanks to the network of sensors already in place. For geophysicists, one of the most exciting prospects is the chance to observe how magma interacts with seawater in situ. The interface between molten rock and frigid water is a zone of rapid transformation. Glass forms, gas is trapped, minerals crystallize, and complex chemical exchanges occur. These interactions create unique mineral assemblages that help scientists reconstruct eruption histories long after the lava cools. The samples collected after the last axial eruption in 2015 revealed intricate structures formed under extreme conditions, data that are invaluable for understanding both Earth's oceanic crust and volcanic processes elsewhere in the solar system. Another layer of intrigue lies in the biological colonization that follows such eruptions. Within weeks, new hydrothermal vents can become teeming oases of life. Bacteria, tube worms, and shrimp species rush to exploit the chemical energy released from the cooling lava. These communities are among the most primitive ecosystems known, often thriving without sunlight and relying entirely on chemosynthesis. Observing how life reclaims these newborn landscapes provides insight into how early life on Earth might have arisen in similar environments billions of years ago. The ongoing volcanic unrest could thus offer scientists a live laboratory for studying the interplay between geology and biology at its most fundamental level. Economically, the eruption potential also brings attention to the growing field of seafloor resource exploration. Submarine volcanoes and hydrothermal systems are rich in minerals like sulfides and rare earth elements, though commercial mining remains controversial due to environmental concerns. The scientific data from events like this help clarify the risks and benefits. Understanding how these systems evolve, how deposits form, and how ecosystems recover after eruptions informs global policy decisions about whether and how to exploit deep-sea resources responsibly. The red alert has also reinvigorated debates about Earth monitoring priorities. While satellites provide unparalleled views of surface changes, the ocean remains one of the least observed regions of the planet. The current unrest highlights how much activity can unfold unseen beneath thousands of meters of water. Some experts argue that more investment should go into ocean floor observatories, not just for volcanology, but also for earthquake early warning, tsunami detection, and climate studies. After all, the majority of Earth's volcanic activity occurs underwater, yet we observe only a fraction of it directly. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Oregon's submerged volcano suddenly shaking with thousands of quakes? We want to hear from you. Thank you for watching and see you next time.